Okay, so what we are going to be doing right now is we're going to talk about Unit 7, Worksheet 4, Orbital Motion. Problem number 4 is talking about a historical case. So back in Galileo's day, he was an astronomer back in the 1600s. One of the objections to the heliocentric model of the solar system is that if the Earth is spinning, we should all be thrown off the Earth. Now the truth is, you do weigh a bit less on the equator than you would at the poles. Our job is to calculate how much. The hint is to construct force diagrams for a 100 kilogram person standing on a bathroom scale at the equator and at the pole, and then do the F-net calculations. So I'm going to first show where the poles are going to be. So right up here is one of the poles, and this is the other one. The Earth spins about the poles. So that way a person standing at the pole is just going to spin around and around and around. It doesn't matter what time of day it is, they are going to still be at that same spot. However, a person standing at the equator, more or less right here, anywhere along this, while they're going to be standing on the equator, and they're going to still be standing in the same spot, for example, right now they're standing in Africa, 12 hours from now, or half a day later, they're actually going to be spinning around. So Africa and them would be over here when the Earth is spinning. So what this means is that when we're talking about a person at the poles, there is going to be no circular motion. However, when they are at the equator, they are going to have some circular motion. And I'm just going to try to keep the colors consistent. Equator. There is circular motion. Now I'm going to draw two force diagrams, one for a person standing at the pole, and the other for a person standing at the equator. In order to make sure that we can compare the different apparent weights between these two, I'm going to be drawing it so that way they are both standing straight up. So when there's no circular motion, the person standing at the pole is going to be undergoing no net force. There's nothing causing them to either change their position or have a change in motion. So I'm going to leave that as a net force of 0. So I have a force of gravity acting on the person by the Earth pointed down, and I'm going to have a force normal acting on the person by the ground pointing up. And I can say that those two are equivalent because, well, our net force is going to be 0. However, for a person on the equator, they are going to have a net force because they have a centripetal force. That centripetal force, doesn't matter where they're at, is going to be pointing to the center of the Earth. So if we're drawing it so this person is standing straight up, that means that they're going to have an overall net force pointed down. We're still going to have the same force of gravity acting on them, on the person, by the Earth. And because we can assume the Earth is pretty spherical, where it's pretty consistent with the distance from the center of the Earth to wherever they're standing, we can even say that this is going to be equivalent. What is going to be different, though, is going to be the normal force. I'm drawing it smaller because overall our net force needs to be pointed down here. Whereas at the pole, it's pointed, well, nowhere. It's going to be 0. Because when we're talking about our weight right here, weight is really going to come down to how much the force of gravity is acting on you. But the problem here is that our force of gravity is the same. So instead, we can think about the differences between our normal force, which is what we use when we're trying to talk about how something weighs. And I put that in those quotes because it's not their actual weights, it's just how much they're currently weighing. Or another way to think about that is the apparent weight that this person has. So this right now is just going to be a qualitative force diagram that we have down here. In order for us to actually figure out what the difference in their apparent weight is going to be, we need to quantify it. Now, to keep the math simple, we are going to just be assuming that the mass of the person is 100 kilograms. So I'm going to be separating my force diagrams from my calculations. That's what I'm going to have on the right. The first force we can always quantify is going to be a force of gravity. Our equation for the force of gravity for an object pretty near the surface of the Earth is 9.8 newtons per kilogram. And that will be multiplied by the mass. This person has a mass of 100 kilograms, so overall they have a force of gravity of 980 newtons. So I can add that right down here. I can add that because it's equivalent to my normal force up here. And because this is going to be the same equation I can use for the person at the equator, I can add that same number down here. There are so many different places that we can put this. However, we cannot use that equivalency to figure out our normal force. So we're going to need to figure out what our net force is going to be, or in this case, our centripetal force. So our centripetal force, we can use the equation mass times velocity squared divided by the radius. This is our equation for centripetal net force. We know the mass, and we need to try to figure out what the radius and the velocity is going to be. Now, when we're talking about the radius, this was actually given to us in one of the other problems on this worksheet. We know from problem number 3 that the radius of the Earth is 6.38 times 10 to the power of 3 kilometers. Now, in order to convert that to meters, which we'll need to do, we'll multiply that by 1,000 meters for every 1 kilometer. So that way, this radius is 6.38 times 10 to the power of 6 meters, or that will be 6,380,000 meters, if you don't want to work with scientific notation. So that's what we can use, well, right up here. But we still need to figure out the orbital velocity. Now, the orbital velocity is the same thing as our speed, which is going to be the distance traveled divided by the time. Now, the distance of a circle is going to be the same thing as the circumference, 2 pi r, and the time it takes for this Earth to rotate once is going to be 1 day, or 24 hours. So, in order to figure out exactly how fast this thing is spinning, we'll just plug in some numbers. 2 pi, 6,380,000 meters, all of that divided by our 24 hours, but we also need to make that sure that's going to be in seconds. So we'll multiply that by the number of minutes in 1 hour times the number of seconds in 1 minute, so that way we can figure out exactly how fast the Earth is going to be spinning. Now, for this one, when we plug this in, the 2 times pi times the r, the 6,380,000 meters, will give us a really, really big number. Then we would need to divide that by our 24 times 60 times 60. So overall, this person is going to be spinning with their orbital velocity or speed at a rate of 464 meters every second. So we're going to take this velocity and this radius and go back up here in order to figure out what our net force is going to be. So our net force is the mass, 100 kilograms, times the velocity, 464 meters per second. All of that gets squared, divided by the radius of 6,380,000 meters. So when we plug that into a calculator, we are going to have an overall net force of 3.37 newtons. So over here, back in our actual force diagram, we can quantify that net force. We have 3.37 newtons acting as our net force. We have more force down than we have force up. So our normal force is going to be 3.37 newtons less than 980, which is going to be about 976.63 newtons. No, sorry, wrote that backwards. So when we're trying to figure out the difference to answer this question, we're going to be comparing those two apparent weights, our normal forces. Or the difference to answer this question is there's a difference of 3.37 newtons. So at the equator, you weigh 3.37 newtons less than you would at the poles. Or rather, we should say you feel as though you weigh 3.37 newtons less.